Kelsey, and this is Steve Durst. And Dr. Chen, Linji, are you there?
Yeah, I'm here.
Oh, aloha.
Hello, hello.
Good morning. Aloha from Hawaii. And
Okay.
I guess it's must be about 11 p.m. on Monday, June 1 in China there.
Yeah.
And I will make my presentation after Dr. Chen's, and then Dr. Jack Burns, very thankfully, will be making his presentation. I know that Jack has been at this longer than I have, and I've been at it for 30 years, aiming for astronomy from the moon. It's very satisfying, promising, and I think developing, almost inevitably developing, I like to think, new frontier for astronomy, and a new activity and new light industry, I like to call it, astronomy from the moon, a new light industry from the moon. So we'll be making these three planned presentations and others. There's Linji, good morning. And then we have a surprise presentation from the Lincoln Hills Astronomy Group representative Lawrence Lapin. And Lincoln Hills is in California, is it, Lawrence?
It's near Sacramento, yes.
Okay. Well, that's a pretty good spread from Colorado to California to Hawaii to Asia. So I don't know if there's anything else that we need to discuss. I'm very pleased to have this opportunity, and want to thank the AAS for putting on these wonderful conferences and granting us this special session on astronomy from the moon. Kelsey, is there anything else that we need to do before we begin the session?
No, we should definitely get started. We're about 5 minutes behind schedule now.
Well, excuse me, my first time through. Okay, Linji, you want to make your presentation then? Dr. Chen is. Let me just say again, he's participated in a number of our programs, our Galaxy forums, with the subject astronomy from the moon, and he's a astrophysicist at NAO, National Astronomical Observatory of China, that's partnering with the Netherlands, Radboud University, and other scientists on the low frequency explorer on the Chang'e-4 lander, which landed for the first time in human history, anything landing on the far side of the moon, soft landing. So we're very happy and pleased again, Linji, to be working with you, and look forward to the update. Thank you.
Okay, thank you, Steve. Okay, can I see the screen? Hello, can you see the screen?
Linji, we can see your screen. You just need to start the presentation.
Okay, sure. Okay. Good morning, everyone. I'm Linji Chen. I come from the National Astronomical Observatory, Chinese Academy of Science at Beijing, in Beijing. Here I will introduce the Netherlands China Low Frequency Explorer on behalf of all the NCLE Scientific team. Here the outline of my talk. We know this shows the Chinese lunar exploration program for the Chang'e. Now we are, on Chang'e 4. At that time, I think China opened the Chang'e-4 mission for the whole world to call for some proposal. For that one, we collaborated with our Dutch colleague to present a very low frequency radio instrument on board the Chang'e-4's relay satellite. So this relay satellite will be launched to the Earth Moon L2 point. It will build a communication bridge between the far side of the moon and the Earth. This relay satellite will be launched to the L2 point. It operated at a hollow orbit around the L2 point. in 2016, in the beginning of the 2016, the NCLE was really began. We signed the cooperation agreement at Beijing. And here, yeah, you can see this is the Dutch peer and the Chinese peer. This is kind of like, yeah, you know, you may know that, know him, yeah. But why do we propose this instrument? As we can see here, this is the whole electromagnetic spectrum observed in radio astronomy. We can see at the low end of this the spectrum, we call it a very low frequency, also call it ultra long wavelength. The frequency is below 30 megahertz. The wavelength is more than 10 mid. At this frequency range, due to the Earth's ionosphere, the reflection and the absorption, we cannot get it on the ground. So we have to go to the moon, go to the space where we put it on the lunar spacecraft. Here's the main scientific objective for the NCLE. There's several sky mapping and the solar bursts, and also like include also some planetary science. There's also some technical objective like the IFA, the Earth's IFA characterization and the galaxy background, the Earth's AKR or KTN observation. Besides this, there's some also, we hope we can do some potential science like the constraining the dark age and the cosmic dawn observation, and also like the radio transient pulse or something like that. And this is the design baseline for the NCLE. The frequency band is from the 80 kilohertz to 80 megahertz. It has a 3 orthogonal module antenna. The total power should be less than 50 watt, and the total mass should be less than 10 kilogram. This is the dimension, and the lifetime is around 3 years. At first, we estimate the sensitivity of the NCLE. We suppose the ILOA has a noise of 230 Kelvin, and the frequency band is 10 kilohertz. This 3 black line shows the sensitivity with different integration time. The first one, the upper one is 1 second, 1 day, and 11 days. We can compare. We can see it's compared with some other radio emissions flux here. And after the design, we recalculated the NCLE's sensitivity. It divided in the design. We divided NCLE to 3 bands. The first band is less than 3 megahertz. The second one is 1 to 60 megahertz. The third one is 60 to 80 megahertz. As we can see here, for different frequency band, it has different sensitivities. Here shows the galaxy background. As we can see here, from around 2 megahertz to 50 megahertz, it can achieve the sky noise limited. This shows the whole schematic diagram of NCLE. In the outside of the platform, it includes the antenna and the deployment mechanism. Inside of the platform, there's the AAA and the analog input system, the calibrate, and the digital receiver system. Here also we have the power supply unit and the command and the data handling system. Here is the Chang'e-4 relay satellite. Here is the antenna design and some tests. This antenna is made of the carbon fiber. This carbon fiber antenna coiled around a ruler. It will drive by a motor. When deployed, the motor can drive the ruler to deploy the antenna. For this design, there's one advantage. When we want, we can deploy the antenna. We can also retract the antenna back. So. This shows the different component of the NCLE inside the different box, inside the E box and the LNE box. Just show it. This is the whole system, and this is where they are inside this E box and LNE box. Here's the whole NCLE specification. It mainly, the NCLE mainly includes 3 parts. This is the antenna, this is the LNA part, and this is the e-box. It has the digital receiver and some controller unit. The NCLE includes 3 5 meters multiple antenna. There's 3 band, and the maximum it has a 16 kilo channel. And it can achieve the scan-out limited between the 2 to 50 megahertz. We can observe the 4 polarization. The ADC is 14-bit sampling at the 120 megahertz. The onboard memory is around 250 gigabyte. The downlink speed is less than 10 megabit per second. The total power is less than 25 watt, and the mass is less than 10 kilogram. Here's the signal processing and the scientific mode of the NCLE. Basically, it has 3 scientific mode: the spectral mode, and the beamforming mode, and the trigger mode, and the VLBM mode. Here we have the 3 antenna channel, and here this is another calibration channel. And also we can see here the different frequency, but different scientific mode, and this is spectral beamform mode, and the trigger mode, and the VLBM mode, and then the output the measurement result, and we compared with this 3 antenna channel with and with the calibration channel to calibrate this the whole system. This is some test for NCLE, the FM model. This is the test. This test was done I think in Netherlands. And in 2018, the NCLE was installed on the relay satellite platform. Here is we tested the half-meter deployment in the launch side. This is the outside of the platform. This is the antenna. This is the e-box. Is inside the relay satellite. On the May 21st, 2018, the NCLE was launched with the relay satellite together. On the June 13th, it arrived at the operational orbit, the L2 orbit. And after that, we do some commissioning tests. This is several important time points for the NCLE test. The first switch on was done on the January, and on the February we do the first spectrum observation. On the June we do the first long duration observation. In the November we did the antenna deployment. Here's some commissioning phase test. Yeah, this is some auto-correlation result for the 3 antennas. This is some cross-correlation result. Yeah, this data was observed. Yeah, was obtained on the February in 2019. Yeah, last year. Yeah. This is some other test on May last year. This is also yeah, autocorrelation and cross correlation. We can see here this like a comb, a spectrum. This is the calibration signal. This calibration signal is generated by the clock of the NCLE. And in November we deployed the antenna. This is the antenna photo. Just before the deployment, yeah, this is the photo with for the NCLE with the moon and the Earth together. Yeah. Here's the deployment. In the November, we deployed the antenna. First, we deployed my antenna for half meter. After that, we confirm it, and then we deployed the antenna to 5 meter. But unfortunately, all these 3 antenna was not deployed fully. The first one is just deployed to 4.1 meter. The second one deployed 2.1 meter. The third one deployed 2.8 meter. We are still analyzing what's the problem with it and try to find some solution to redeploy it again. Here in the final state, we can see this is the third antenna. We can see here, this is the other two antennas, the other two deployed antennas. After the deployment, we just before the deployment, we also did some observation, and this is the X antenna and Y antenna calibration. This is auto correlation result. This two plot shows the X and the Y. This is the calibrate, and this is also the cross correlation. This is also, I think, auto correlation. This is for the X, and this is the calibration, and this is the calibration channel of the signal. Yeah. Here, this is some other, I think, some other observation result with different ILOA configuration. Here is for another frequency band, 60 to 80 frequency band. Here we can see, but here we have a 1 megahertz low pass filter. We can see here, this is some signal below 1 megahertz here. And I think at first we just focus on, because the antenna was not deployed, so we just focus on to do the calibration for different configuration, system configuration. Yeah. Here is here is some result for the before the deployment and after deployment. This is only for the half meters antenna deployment. Here we can see some difference. This is before deployment. This is after half meters deployment. We can see that the signal, I think, increased some, but this is just a very preliminary analysis. We are now still analyze the data to get more, I think, information from it. Yeah. Okay, here's the summary of my talk. So NCLE is a pathfinder instrument on board the Chang'e-4 mission, and also the technical demonstrator for the future space very low frequency radio telescope. It's aimed to open up the last unexplored radio regime and has been launched in 2018. NCLE has finished the commissioning test, and the antenna have been deployed, and the observation data is still being analyzed. And it will observe the sky at low frequency, detect the planetary radio emission, observe the solar radio burst. Technically, it will also do some Earth's IFI-AKR measurement. And so you will also try to study some potential signs like the dark age 21 centimeter emission, and there will be observation with the Moon Earth baseline. Okay, thank you all your attention.
Very, very interesting. Thank you very much, Linji. I don't know if it's appropriate that we invite a question or two. Is that a usual procedure, Kelsey?
So the audience, the attendees can submit questions through the Q&A. Currently, I'm not seeing any questions in the Q&A, but I can post in the panelist chat if one comes up.
Can the participants, the 3 or 4 of us, ask questions directly?
Oh yeah, absolutely.
Well, very exciting, Linji, to actually be doing astronomy from the far side of the moon and opening up that dimension. I know that Professor Burns has been at that for a long time and has many programs and ideas and that we'll hear shortly about that. Can you tell me how long the mission is planned for, and what you mentioned that the antennas are not fully deployed, how long will the efforts be made to have them fully deployed?
Yes, I think the expected lifetime for this mission is 3 years, but we guess for the relay satellite, yeah, we learned from the platform college. They told us that the platform can I think work for 5 years, even longer. So I think if the platform can work, I think this instrument will also can work for that long. And the second question about the antenna deployment, yes, I think the antenna was not deployed fully. I think there's some problem. I think when we deployed the antenna, it was stuck. Yes, for all these 3 antennas. The first one deployed longer. It's 4.1 meter. 4.1 meter. The second one is 2.1 meter. The third one is 2.8 meter. And it's stuck. We try to increase the speed and motor speed and to increase the force, but yeah, it's kind of stuck there. We are after that we are still analyzing it. We have a FM model backup in the lab, so we are trying to use this FM backup to find some solution to see what happened, and try to find some solution to maybe.
Yeah, let me if I could, Steve, let me ask Dr. Chen with regard to the antennas. So do you think that the problem with the deployment might have been the fact that the antennas were stowed longer than you originally had anticipated, and maybe thermal effects affected the deployment mechanism?
Yes, I think, I think, at this, I think at this point, I think maybe the problem with deployment mechanism, because it's kind of just like the, how to say, yeah, I think it's stuck inside the.
Yeah, it's a little bit of a surprise because these kind of stator antennas have been deployed many, many times in space before, and the failure rate has been very low. So I realize these antennas are a little bit different than what has been done before, but yeah. You now have 3 antennas, 3 monopoles that are at different lengths. So yes. How is that going to affect your data analysis now? That is not certainly what you were anticipating.
Yes, I think at first we want to use these 3 antennas to do some beamforming to make it mapping and make the sky mapping. But now I think with different length antenna, I think it's not happy, I guess. But for different lengths, we have different sensitivity. Yeah, you can see. Yeah, for at a different frequency band, it is not a very bad thing, but we can use these 3 antennas to focus on different frequency band. Like the 2.1 meter, we can focus on around 70 megahertz, like that. And yeah, we will lose some sense, but we still can get some very useful, I think, data from it. Yeah, with these 3 different length antenna, I guess.
Well, we all hope so. We're very much looking forward to those data.
Yeah, we also hope that. Yeah, but still, yeah, due to this coronavirus stuff, yeah, we cannot do it now. But now, next month, we will begin the new observation. Yeah, it will, postponed for several months already. Yeah, good.
Well, that's
Steve. Do we need to move on now?
I think so. So just one concluding question to Dr. Chen. You said 5 years. Now that's the projected mission for Chang'e-4 lander. And are there other?
No, for the lander, the lifetime is expected lifetime is half a year, but it's already
so the 5 years is for orbit then.
For 5 years, just for the relay satellite.
Yeah. And are there any future research plans for low frequency astronomy that NAOC has to follow through?
At this point, I think we have another project. I think low frequency. I think Checkpoint also attended that forum. I guess is it a DSL? It's a lunar orbiting. I think very low frequency array. It include 8 or 7 or 8 macro satellite, and it's already in the engineering study. Next time it may be do the real, I think.
Well, good luck on that, and thank you so much. It's almost midnight there, and thank you so much, Linji. I'm looking forward to more data, as Jack mentioned, and more progress from NAOC and your work. So thank you so much.
Okay,
and
thank you.
Now, so to move along, as mentioned, I'll be making the presentation from our organization, the ILOA, the International Lunar Observatory Association. And if I can call that up, how do I do that? Kelsey or Dan, can you help me bring up my PPT?
Yeah, in the bottom middle of your screen, you're looking for a shared screen.
Yeah.
Go ahead and click on that.
Okay.
And then we're going to select the PowerPoint deck.
There it is. Great. All right. Well, thank you very much. Thank you.
Okay, great. We're seeing it.
Yeah. Okay. So, quite different than an actual in lunar space presentation, a technical update that that Dr. Chen has presented. I'll give a brief couple of comments about astronomy from the moon, the purpose of our session here, and some details about our organization, the International Lunar Observatory Association, based here in Hawaii, Kamawela, Hawaii, right next, just a few meters away from the Canada-France-Hawaii Observatory facility. And then go through a survey of some of our activities internationally regarding lunar astronomy, and end up with the update from USA, and turn it over to Dr. Burns for his presentation after mine. And then assumedly, if we have enough time, Lawrence, you'll have time for a presentation too, if you're prepared for one. I'm not sure. So ILOA, okay, why astronomy from the moon in general? And of course, the participants know well these assets for the Farside presentations. Farside astronomy, of course, the moon provides a unique shield against radio frequencies coming from Earth, providing a great radio quietness, and the Farside for VLF and Dark Ages initiatives. The moon is a great platform for long duration observation, very, very stable, large area, favorable to interferometric build-outs. The exosphere, extremely thin, even thinner than LEO, which a lot of people don't know. So there are advantages to lunar observatory in terms of the vacuum of space that is even superior to that of LEO. And then, of course, one might not be going to the moon just to do astronomy, but one, as we return to the moon, and we are doing that robustly now, finally, astronomy observation will be one of the most fundamental and inevitable activities to look out, to observe, to do astronomy. In fact, astronomy is likely to be, as I mentioned earlier, one of the first industries from the moon, a light industry, as it were. From It's possible, of course, on this new frontier, this new world of the moon, we can make observations of various kinds with various wavelengths from using various instruments from any place on the moon. Our organization, and as far as astronomy from the moon, in this next year, there are a number of venues that we're involved in, events. We're collaborating with the Royal Society's postponed event from March. They're helping us with an event in Europe with the theme Astronomy from the Moon in Vienna, and we'll be helping them when they reschedule their postponed event in London. We're here today, of course, at this special session on astronomy from the moon, and you'll see we have a number of other venues for the rest of the year that are either confirmed or in process of being confirmed and organized, with a strong focus on astronomy from the moon. Galaxy Forum is our outreach mechanism. We've had 97 of them so far. The last one, perhaps the most productive, was in Chiang Mai, Thailand. Maybe I'll have a little bit more to say about that later. That was in early March, before the health emergency got difficult. We were very lucky to pull that off, thanks to the Princess of Thailand insisting that we go through with the event. So astronomy from the moon. ILOA has a mission to expand human understanding of the cosmos through observation from our moon with Aloha. How we go to the moon is important, as important as that we go. We were founded in 2007 here on Hawaii Island, which is host to 13 world-class observatories. The organization is constituted by 27 highly distinguished international directors, and there's a day-to-day executive committee that operates from this office here in Hawaii. Our mission is dual function. Well, it's multifunction, but two in particular: observation, in particular astronomical observation, but not exclusively, but observation and communications. And of course, we are going to the moon to participate in the development of a multi-world civilization, to participate in lunar-based build-out, which can be catalyzed by these first functions of observation and communication. I mentioned astronomy from the moon as a first light industry. I should say the imagery that you see below is the photo, the image that was taken by the Japan Kaguya orbiting satellite in 2007, showing the destination that we're aiming to put our flagship ILOA, it's called, mission on Malapert Mountain. That's in the center of the image below, with the Earth rising in back of it. That's an actual photo, and the artwork on top is a stylized image of the ILO operating on Malapert Mountain, taking its first light from the Milky Way and transmitting the image back to a global audience on Earth. Many other functions, but that's the first image, as I mentioned. And let me go through the extent of our operations. That's our flagship mission is to Malapert. You see the artwork there. That was also done by Michael Carroll. We are hoping, almost racing. It's a great incentive to get to one of the more valuable places, not just in the moon, but in the solar system. This 5,000 meter peak at the South Pole, not far from Shackleton. We have last summer, a long anticipated or long appreciated idea of functioning with a backup. We always thought NASA functioned best with a backup from back in the Pioneer and Voyager days, the Viking Mars days, Mars Explorer days. Backups work well, as the China Moon program has also proved with Chang'e 1 and 2, Chang'e 3 and 4. Now we're looking at Chang'e 5 and 6. So we have a ILO2. We'll be building sets of instruments for both. And again, we have a great urgency to get to Malapert Mountain and begin our not just our observation, but our communications functions as well. The precursor on the lower left there, ILOX, the instruments consist of two 2.5 centimeter lenses that'll be mounted on either side of the Intuitive Machines Nova C lander that we are working to conclude that contract. In fact, we had meetings this morning with Intuitive Machines based in Houston and our prime instrument developer Canadensis of Ontario, Canada. And that mission is to go, well, hopefully in 2021, the second part of next year. October is the nominal launch date for the Intuitive Machines' first mission to the moon. And we will be, with our two little lenses mounted 180 degrees opposite on the top of the lander, hoping to obtain the first image of the Milky Way galaxy ever from the moon, hopefully across the lunar landscape, and delivering an iconic image. Before even that precursor, we did have the great experience of operating from the moon on the first robotic lander on the moon. I'll have a little bit more on the LUT, the Lunar Ultraviolet Telescope, aboard the Chang'e-4 lander, which landed in late 2013, and we conducted in collaboration. We have an MOU with NAOC since 2006, and we were able to image the first spiral galaxy ever from the moon using the China LUT, and we hope to be involved with additional lunar-based astronomy, Chang'e-4 or others. And finally, from the beginning, we've been interested in human moon missions, are really thrilled by the fact that we, as far as I'm concerned, the administration got exactly right, sending the first woman soon to the south pole of the moon. Exactly right. I think it's a whole new generation that will be motivated and energized by that mission as soon as 2024. Mission objectives. I mentioned the galaxy first. The first image of the Milky Way ever from the moon. We'll tilt our ILO1 camera down to catch the Earth for long duration Earth observation for climate change, rotation of the Earth and more accurate values for recession, and then tilt our camera further down to image the local surroundings and help develop imagery for the lunar base build-out. And again, many other applications we all know from the moon are possible. VLF we just heard about, and we'll hear some more. SETI, observing Earth approaching objects that are blocked by the sunlight, by coming in from the sun, and solar weather. South pole of the moon, our destination for many assets in the South Pole, and particularly Malapert Mountain. We have 24/7 line of sight to Earth for observation and communication. Also observation to other lunar sites such as Shackleton Rim. At Malapert Mountain, nearly continuous sunlight for power. We all know about the so-called peaks of eternal light. The proximity to the ice water traps at the bottom of craters, to proximity to water ice and permanently shattered craters. Aitken Basin, that huge, what is it, 2,500 kilometer basin, which is a treasure trove for geologists as well as miners. That issue is going to is being joined now. The southern skies, object-rich southern skies, including the Milky Way, are an asset of the South Pole. The experience we have operating on the South Pole of this world should help us operating on the South Pole of our closest neighbor. And as I mentioned, that's our goal. to get that first image of the Milky Way from the moon, with the hope that it'll provide inspiration, direction, motivation, a sense of awe, similar to the first image of from the moon in the 20th century when we look back at Earth. Now in the 21st century, we stand on the moon again. We will be looking out towards our future. I think I'll take maybe the last 7 or 8 minutes to survey other astronomy from the moon developments, some of which we've been involved. These are very early ones from our our senior astronomer, who I know Dr. Burns knows, Yuki Takahashi, has been with ILOA from the beginning. He's in Japan now. He did early studies on Farside and Malapert Mountain Observatories, South Pole Observatories. Yuki went to Antarctica to do astronomy 6 different times. Currently, we've heard about the China-Netherlands Low Frequency Explorer, and Dr. Burns has been taking initiatives for Farside astronomy for many years, and those are just a few of the examples of his work. The Dark Ages Radio Explorer, the Lunar Consortium. We'll hear more in detail shortly. China, I mentioned we've had an MOU since 2006 with NAOC to collaborate on astronomy from the moon. They were fortunate to land the first robotic telescope in 2013 on the northern latitude, I think about 41 degrees north. A little difficult for imaging the galactic center, but we did image. I'll show you momentarily. We did get some images. The LUT has been very productive. There's a lot of data that has not been processed, and our organization, ILOA, is working with NAOC to fund a researcher to begin processing a lot of that unprocessed data and publish papers about it. On the bottom right is the early LUT, Dr. Jinyan Wei in the center there. A year ago, just a year ago in April, we had another MOU signed with Professor Shui, seated next to me, signing an MOU. That's Dr. Wei, the principal PI, principal investigator of the LUT in the background, and Dr. Maha Wang, who's another board member at the MOU. This was last April. Because of the health emergency, we have not been able to start. We've identified a researcher for a 2-year contract funded by both of our organizations to process the LUT data. You'll see on the right side of the screen, the Chang'e-4 lander on top, the LUT. It's only a 15 centimeter instrument, 15 centimeters, the LUT. It's on the left as you look at the LUT. And on the center there is the first image of a spiral galaxy ever obtained from the moon with the LUT that our astronomers here in Hawaii collaborated with the LUT team to get that image. There are some of the specs of the LUT instrument itself, as I mentioned, 15 centimeters and the 1.36 degree field of view. Scientific objectives: monitoring AGN, variable stars, binary stars, and a sky survey that's not totally complete. I mentioned we just concluded probably the most productive of our 97 galaxy forums to date at Chiang Mai at the Princess Siranthorn Astro Park. It's a remarkable woman that's pioneered an observatory on the top of Thailand's tallest mountain, and an astro park, which is basically an astronomy village unique to the world. We've invited her here to Hawaii to visit Mauna Kea. She's very supportive of the next frontier of astronomy, and Thailand and Southeast Asia having a role in that, in astronomy from the moon. That's the symbol of, that symbol on the left of the red and yellow is the symbol of Southeast Asia. Singapore, we're using its commercial hub center to develop lunar commercial communications. And we have a director there who's on contract to push forward. We'll have our first workshop focusing on the interrelationship between astronomy and communications, and ultimately lunar commercial communications, with Singapore as the hub of Southeast Asia for this. Indonesia, largest country in Southeast Asia, is trying to establish its own 4-meter, the information there is not correct, it's a 4-meter telescope that they are going forward with, and developing a spaceport. Indonesia straddles 1/8 of Earth's equator, which is, as we know, the optimal launch site because of the spin of the Earth. And there's back in Thailand, that's a picture of the Astro Park, the top left, really remarkable. India, we are working with the chairman there, and the previous chairman expressed an interest in astronomy from the moon. They're very interested in maybe not Chandrayaan-3, which is underway, but we have ongoing discussions about collaboration for astronomy from the moon with India. And Japan, Japan, as most of us know, has advanced facilities here in Hawaii, on the other frontiers of astronomy in Chile at ALMA, and lower right in Antarctica. Those are Japan lander plans. The lander called SLIM, that's the acronym for South Pole Lander in 2022. Some collaboration with India. And very briefly, Korea, Russia, that we work with, European Moon Village colleagues, and especially Canada, our closest neighbor, who's building our instruments, Canadensis, and we work with the Canadian Space Agency also very much. Finally, tribute to the pioneer, the father of astronomy from the moon, our emeritus director for many years, Commander John Young, the only person to travel, the first person to travel to space 7 times, including once from the moon, brought the far ultraviolet spectrograph you see on the lower left, developed at Johns Hopkins by George Carruthers. You see him on the top left. And John did experiments on the Apollo 16 mission. On the center image on the bottom, you can see the spectrograph in the distance, and the one of the 170 some odd images was the Earth's geocorona on the bottom right. Finally, USA is going back to the moon. The Artemis program and lunar commitments are moving on despite the challenges, despite the health challenges. The same with the China and space program is moving on robustly. Artemis is growing branches, growing roots, developing various programs, and we'll finish here. Just an aloha to everybody watching at AAS, and my associate panelists here. Come visit us in Hawaii when you can. So that's my snapshot, and I think we have time for a question before Dr. Burns' presentation.
We are about 8 minutes behind time, so a very quick question, or we should just move on.
Okay, well, thank you, Kelsey. We thought we thought we'd only have 3 presentations, and Larry Lappin's presence was unexpected, so we'd be ahead of schedule with that consideration. But Larry, do you have a presentation available? Is that what you're preparing? Are you prepared to make a presentation?
Yes, mine will be short, 5 minutes.
Okay, all right. Well, as Kelsey said, I think we're okay to begin. If there's no other questions, I want to thank you for your attention and for your patience in any mistakes that I made on my first Zoom presentation. Thank you. And Dr. Burns, low radio frequency astrophysics from the far side of the moon. How cool. Thank you.
Yes, thank you, Steve, and thank you for the opportunity to present at this special session today. This morning, what I want to do is to focus on how we will go about opening the last window to the electromagnetic spectrum at low radio frequencies from the far side of the moon. And part of the way I'm going to go about demonstrating this is through a NASA-funded design study that we completed this last year in collaboration with JPL for an array of low-frequency dipole antennas on the surface of the moon, a cartoon of which is shown here on the right side of the first image. So these observations will take place between 100 kilohertz and about 40 megahertz or so. The thing that's interesting to note is that even before the first Apollo mission, there were designs that were put forward for a lunar observatory. At the very first workshop on lunar science in 1965, there was one paper published about an observatory on the moon with one dipole on the surface of the moon and several more in orbit that would then be combined together to form a small VLBI array. The recognition of the moon, and particularly the far side of the moon, as a truly unique, in fact, one-of-a-kind location in the solar system to be radio quiet is really illustrated here by looking at the radio frequency environment. Dr. Chen talked a little bit about this. On the Earth, you see from LOFAR observations, European array. This is power versus frequency. That as one gets below 30 megahertz or so, there's a lot of radio frequency interference, mainly coming from powerful transmitters, from satellites. And when you couple that with the issues of the ionosphere and the interaction of telescope beams with the environment, makes it very difficult, if not impossible, to operate from the surface of the Earth. And certainly when you go below 10 megahertz, the plasma frequency of the Earth's ionosphere, it's really impossible to operate. Going into space alone, though, is not the cure. As you can see here in the lower left-hand corner, this is NASA's Wind Waves telescope. And what you're looking at is a dynamic frequency, a dynamic spectrum. This is frequency versus time. And these data were taken when wind waves was in the vicinity of the moon, but not behind the moon. So this is when the Earth was still in view, but at the distance of the moon. You can see these horizontal stripes here, which represent radio frequency interference coming from terrestrial transmitters. The Earth still remains very bright at low frequencies from RFI, as well as at lower frequencies from the auroral kilometric radiation. So when you do go to the far side of the moon, as was true with NASA's RAE-2 satellite in 1972. Here on the lower right, you're looking at relative antenna temperature versus time. This part of the plot shows when the satellite was behind the moon in the radio quiet region. Here you're seeing only the galactic foreground. And so it's been demonstrated to be a truly radio quiet location. So why has it taken us so long, recognizing this, to begin these observations from the moon? Well, of course, first and foremost has been access since 1972. That's changing dramatically now, not only with NASA plans, the China plans, but other international plans. But also in addition, when it comes specifically to low frequency, what has been lacking up to this point in time is something that I like to call a killer scientific app. That is an application, a science application that has compelling astrophysics, which uniquely requires low frequency observations from the lunar far side. And in the last few years, two very compelling science cases have emerged. One is at the early universe, the so-called dark ages and cosmic dawn, here using highly redshifted 21 centimeter observations redshifted to low frequencies. We can uniquely probe and test the standard models, lambda CDM cosmology, in an unobserved epoch, as well as to observe the true first stars and galaxies at redshifts between 50 and 100. The second equally exciting case is one that has to do with exoplanets and habitability. A little bit of an extension of the plenary talk that we heard earlier this morning for the Catholic lecture. But in this case, it's a new aspect of habitability, looking at the space weather environment and whether or not exoplanets have magnetic fields. Those are aspects that may be essential to understanding habitability, and we can do this uniquely at low radio frequencies. So again, what I'm going to do is to focus on this design study that we completed this last year for an array that we call Farside. Farside array for radio science investigations of the dark ages and exoplanets. So it's a mouthful, but it spells out Farside. So that's kind of cool. And so here is our full team. As I mentioned earlier, we worked with an outstanding group at JPL. My colleague Greg Hallinan and I worked with outstanding team at JPL and their Team X to do the first engineering design study of an array on the far side. And what the idea was, the reason that NASA funded us to do this is because we wanted to have this submitted and considered by the current ongoing decadal study, and also to see if we could fit this into what astrophysics is calling a probe class. This is a new class of astrophysics missions that would be capped at about $1 billion or so. And I can report that we've been successful in doing that. So what's the science? Well, as I mentioned before, the science here primarily is to look at exoplanets. And here we can gain some perspective by looking at Mars as an example. We know that young Mars was wet. It had a significant atmosphere up to about 2 billion years or so ago. The core, though, cooled, the magnetic field turned off, and the solar wind then began to strip the atmosphere. This is confirmed with MAVEN, where MAVEN observations show that even today the atmosphere continues to be stripped. And Mars was, although it's nominally in a habitable zone, has been transformed from something that might have been Earth-like to a desert planet that we see today, which has a very harsh environment on the surface. So a combination of understanding the space weather and whether or not there's a magnetic field to protect the atmosphere may be important ingredients for habitability. Here is a movie that my colleague at JPL put together. This shows a coronal mass ejection. On the left-hand side is the impact on a Mars-like planet. On the right-hand side, an Earth-like planet. The difference, of course, is the magnetic field. The magnetic field protects us and has protected life on the surface. In addition, though, when there is something like a CME that occurs, it lights up the magnetic field, produces an auroral kilometric radiation that we can see at low frequencies. And we can see that also with exoplanets using a lunar Farside array at low radio frequencies, okay? So that shows, you know, there's a cartoon of what we are looking to do. So what is the opportunity? Well, we know that TESS is mapping out, as we heard earlier this morning, the nearby exoplanets. And we also know that the vast majority of stars in our solar neighborhood are M-dwarf stars. They are cooler, and that means that the habitable zone is only out to about 2/10 of an astronomical unit. So you have to be much closer to these cooler stars in order to potentially have water on its surface. But these M-dwarf stars flare. They produce a lot of radiation. Here's a comparison of a large solar flare from the sun, about 45 times larger than normal. And in comparison, a flare from an M-dwarf star, 100,000 times more intense than what we get from the sun. So there's a lot of activity there undergoing these M-dwarf stars. How is that going to limit potentially habitability? So again, we can probe these things using low radio frequencies. Here you see this highly stylized cartoon picture of an M-dwarf star and a coronal mass ejection in analogy to what we see from the sun. In the case of the solar system, the sun produces type 2 and 3 solar bursts that are mainly at frequencies below 10 megahertz, so mainly at frequencies below what we can see from the Earth. And these are shock waves that propagate out, but they emit low frequency radio emission. And then, as I alluded to before, also these shock waves energize the magnetic field, energize particles that cause auroral radio emission. So once again, low radio frequencies is where you want to go. So an example of this coronal mass ejection on the left-hand side is a white light image. On the right-hand side from wind waves shows the dynamic spectrum. This is a frequency versus time, and you can see the CME starting off at about 10 megahertz and then quickly goes below 1 megahertz as that shock wave expands outward, the magnetic field lessens, and the frequency drops. Similarly, for the planets themselves and the magnetic fields, the magnetic fields, all of the planets with magnetic fields in our solar system produce low frequency radio emission. Only Jupiter, though, is observable from the Earth, and we've known that since the 1950s. And the reason is that the frequency of planetary emission is directly proportional to the magnetic field. Only Jupiter has a magnetic field strong enough. Everything else, including the Earth, is below 10 megahertz, below the cutoff for the ionosphere. And Earth produces a very powerful, what's called the auroral kilometric radiation below about half a megahertz or so. So once again, if we want to see exoplanets and magnetic fields, we need to go to a location where these lower frequencies will be accessible, namely the far side of the moon. So for our far side array, here's the requirements that we put together that would permit these kind of observations. 128 dipole antennas. Each antenna is 100 meters end to end in length. This is still electrically short. The frequency range is 100 kilohertz to 40 megahertz. The resolution, the spatial resolution, will be modest, about a degree or so, but still will allow us to separate one exoplanet system from another in the inner part of the Milky Way. And the collecting area is very large here, and reason because dipole antennas have large beams, so that the effective collecting area is 12.6 square kilometers. That is an order of magnitude greater than the square kilometer array. But of course, we're looking at very low frequencies, 2 orders of magnitude below what the SKA can attempt to look at. All right, so where on the moon can we observe? Because there's one factor we have to take into account, and that's diffraction. That is, the low frequency radio emission bends around the moon, shown over here. So my student Neil Bassett and I and colleagues did a recent 2-dimensional numerical electrodynamic simulation, very similar to what Yuki did a number of years ago for his dissertation, and looking at somewhat higher frequencies. And what we find are these regions on the far side of the moon where we have at least 80 dB of attenuation. That is at least 8 orders of magnitude of attenuation. At the higher frequency of 10 megahertz, you can go down to within probably 5 or so degrees of the lunar pole and still be attenuated. But at the lower frequencies, where we want to do the exoplanets, at 100 kilohertz, you have to be further away from the poles and the limb of the moon. But still, you have access to roughly the northern third of the South Pole Aitken Basin, which is an ideal spot for studying geology and the early history of the Earth and the Moon. So Farside mission concept, we'll use a commercial lander that's shown here. It will deliver to the moon 1 or more rovers. We're doing a trade study now on the number of rovers. It will deploy these science tethers that will have communications, it will have power, data relay back to the central station, and then the antenna receiver nodes that you see put out here in this cartoon. We will deploy these over a 10-kilometer diameter in a flower petal-like design. So the rover will go out from the base station, and the red dots that you see here are examples of where the antennas would be placed. The rover would turn back around, reload at the central station, and go back out. So depending on the number of rovers, anywhere from 1 lunar day to 4 lunar days to deploy. The antenna node you see is shown over here, and we've based this, at least in part, the electronics in part, on an approved NASA heliophysics mission called Sunrise, which will be flying in the next 3 years or so in high Earth orbit. It's a CubeSat mission. In our case, we've shrunk down the boxes somewhat. We, of course, include here a science tether, and within the tether is also the 100-meter wire antenna that operates at low radio frequencies. In addition, stationer antenna that's 5 meters tip to tip. This will be for the higher frequency, mainly cosmology observations. The instrument box down here, the electronics, will have both a radiator to be able to cool and operate during the day, and then an RHU, that is a radioactive heater unit, that will allow us to operate at night, because nighttime observations will be our most sensitive observations. Here is an example of an array at the Owens Valley. This is the long wavelength array that Greg Hallinan operates. I show this simply because we've got now very good analogs to low frequency arrays like what we do on the moon on the Earth. This one has hundreds of dipole antennas, does all sky mapping. So a lot of the software development as well as the hardware development has already been done and can be directly translated to the Farside array. So when you put all of this together, and having completed an end-to-end engineering model, this is sort of our science plot here. This is what we can detect. This is flux density versus distance from the Earth. And these are the planets now that we think we can detect their magnetic fields. And we detect them when the equivalent of a CME causes the auroral kilometric radiation to be elevated. And the different colors represent different models of the enhanced solar wind. But what you're seeing here is we've got several dozen nearby planetary systems that are within view to do these powerful observations. We've also been collaborating, I should mention, with Blue Origin and using their Blue Moon lander here. You see an example of their lander. They're able to, they're planning on in the next few years to deliver 5 metric tons to the lunar surface. Here you have several different rovers that one could imagine deploying there. Then a cartoon picture or video of the one lander coming off of Blue Moon, one rover, I should say, coming off the lander here. It will deploy the base station where the lander is. Will have the correlator. It'll have a power source, which we nominally plan as 2 RTGs, radioactive thermal units, and telecom. Here you see the rover also deploying the science tether and one of the antenna receiver boxes, and then the stationer antennas coming out over here. So in preparation for Farside, which we are planning for deployment later in this decade on the moon, recently NASA put out a new call for additional science payloads for small unmanned landers as part of the Eclipse program. And we've been working, again, same basic team at JPL, on a prototype for Farside called PRIME, Prototype Radio Interferometer on the Moon for Exoplanet Studies. Here would be a simple 6-node interferometer, lander located over here, and then the 6 dipoles in an L shape. That gives us a bit of better instantaneous UV coverage to be able to do mapping. It would operate in the same low frequency bands as Farside. We will plan to use the JPL Axel rover, which is a very mature TRL-6 concept that is currently available to deploy the antenna and the rover unit. Using this set of dipoles, what we did is we did a mock observation of a type 2 solar burst. We're going to use solar bursts from the sun and exoplanets, planets in our solar system, the radio mission, as prototypes of exoplanetary systems for this prime mission. Mostly what this will do for us, though, is to help us buy down risk on Farside for things like mobility, deployment, thermal operations, and also understanding, frankly, the interactions between with the lunar subsurface, which reflects some of the emission. So last slide, summary and conclusion here. The moon is open for business, finally, finally. As Steve mentioned, I've been at this for 3.5 decades, and it's exciting now to see NASA, ESA, and the other space agency, China, all dedicated missions to the moon and beginning to look at low frequency observations. The NASA CLIPS programs, 2 missions going to the moon in the next few years will carry low frequency radio telescopes. One will fly next year. My colleague Bob McDowell heads a mission called ROLLS. And then a second one led by Stuart Bale at Berkeley will also put low frequency antennas on the moon. So hopefully then after that, we'll have Prime and then Farside towards the end of the decade. And that will get us in a position to, for the first time, study this new aspect of habitability, whether exoplanets have magnetic fields, and to constrain the weather conditions, that is, the space weather conditions in these systems. So with that, Steve, I'll stop there.
Well, thank you, Jack, for a very comprehensive and thorough presentation on low frequency observations, and citing that 1965 presentation. I know it goes back from the beginning of the Apollo program. This obvious great asset for astronomy, doing astronomy from the moon. And the two, Jack, I have just one question, actually several, but the 2 low frequency experiments that you see coming through the CLIPS program in the next couple of years, are they going next year? I know there are 2 landers next year, and then.
Yes, that's right. In fact, you mentioned intuitive machines and that payload that you're working on right now. Bob McDowell has a mission called ROLLS, which is confirmed to fly on that intuitive machines lander. They are going to be delivering that to intuitive machines later this year for flight, I think, the middle of next year. So we're going to be having, now this will go to the near side, so it's not the ideal location, but nonetheless it will allow us to assess the low frequency environment from the surface of the moon.
Right, that was one of those the NASA science projects.
Right.
And the second one.
Yeah, the second one is called Lucy, and it's a combination of low frequency radio and also carry a magnetometer. And that mission and ROLLS will both do things like measuring the lunar ionosphere, because you can use radio sounding to basically measure the density of the lunar ionosphere, which, as I think you mentioned, Steve, is very, very thin, but still can be measured at low radio frequencies. But also look at type 2 and type 3 radio bursts, and have a gander at also things like Jupiter, which has lower frequency radio radiation than what we can study effectively from the Earth.
Well, very, very exciting. And also that second killer app that you mentioned is a very exciting one also, the exoplanet habitability research. Certainly,
It's
certainly.
really the only way to be able to come at that aspect of habitability. There's no other way to be able to remotely sense the magnetic field. There are other ways to be able to look at the activity of stars, such as in the X-ray and in the optical, but also the radio gives us an opportunity to quantify the acceleration of energetic particles around these stars. And again, that's unique.
Along with, I guess, spectroscopy of the exoplanet atmospheres, which I know is one of the main goals for the big telescope that's projected for Hawaii here, the next generation of extremely large Earth-based telescopes.
Right.
Are there any other questions for Dr. Burns?
Yes, there are some questions in the Q&A. Steve, you also have questions in the chat. If you can see the chat icon at the bottom of the Zoom window, you can type answers to those. In the Q&A for Jack, we have a question. To what extent are you concerned about RFI from the other growing activities on and around the moon?
Yeah, that's a good question. People ask that all the time. And there's good news about that in the sense that the low frequencies that we're going to be operating at are well outside the communication frequencies and their sidebands. But these craft still can produce emissions from electronics, from power supplies, from computers, if we're not careful. But those can be shielded very simply with a Faraday cage that's basically chicken wire inside the spacecraft to reduce those emissions. And if we basically stick to the MIL standards that are being applied for satellites in orbit of the Earth, that will keep things quiet enough. But we still have to be aware of that. You know, everything from international agencies to the UN is considering how we go about putting some new legal framework into place to make sure we continue to protect Farside going into the future. But it's a good question also in the sense that given the history on the Earth, we need to do these observations sooner rather than later before the moon does get terribly polluted.
So we have only 10 minutes left in the session and we do need to move on to Lawrence. But Jack, you have a couple more questions in the Q&A.
Yes, I see those. I'll type answers to those.
Thank you. Okay, well, this is an additional asset to our session. Lawrence Lappin from the, where is it, the Lincoln Hills Astronomy Club in Sacramento. And your title again, Lawrence?
I'm looking at methodology for searching for comets.
From the moon?
No, for Mercury.
Oh, okay. All right. Well, it's a different.
How did I get to the moon project? Well, it's a matter of remote sensing, and in searching for these moving threats, we have to right now search from Earth, and we've got a great big problem here. All of these comets and asteroids are going to the sun, and they're returning from the sun, and we can't see them very well until they're quite far from the sun. And that's the nature of my project. And it's basically the same issue that you're faced with observations from the moon. By having telescopes in space closer to the sun, and we can see these threats to our own planet. And right now we're doing very little. And for some of these comets, absolutely nothing. So I have a prepared talk here, and I'll just briefly go over it. As I said in my prepared talk, we're talking about misbehaving asteroids and comets and upgrading our defense against them. And searching the skies, of course, is our first line of defense against such threats. We'll focus on using space telescopes, also used to track, characterize, and for threat assessment. Okay, I only have a couple minutes here, so I'm going to paraphrase what I've prepared. The big signal that we have a deficiency here is the Chelyabinsk asteroid in 2013. Nobody saw it coming. It exploded over Russia, and we didn't see it coming because it was arriving at an oblique angle and was hidden by the sun. What if something quite a bit bigger were to be hidden by the sun? And that's the whole theme of my project here. And we can duplicate in space much of what we now do on the ground, but we can get around this obstacle of solar occlusion by having instruments far out in deep space. And so we can still sort of emulate what is done now on the ground, but do it within the space observatory itself. And we can adapt one of the favored protocols used by the NASA partnerships, which is to do observational cadence. So if we observe each field 4 times per night with 1 to 2 hours from first to last image, they will bring a tracklet. And each revisit, we 2 more times over the next 21 hours, we get 3 tracklets. And for those, we can get a track and actually compute precisely the orbit of this object. Now, NASA's protocol works very well for objects traveling near the planetary plane, though it's less successful with relatively rare and now neglected space objects. Those are likely the long period comets approaching at oblique angles and originating in the Oort cloud. And as we know, the Oort cloud extends way beyond Pluto and into the limits of the solar system. So I'm proposing here putting 3 telescopes in Mercury orbit, near Mercury. Now, one would be on the night side of Mercury. The other would be 60 million miles away or 70 million miles away on the other side of the sun, but also in the Mercury orbit. And the third telescope would be on the sunny side of Mercury. And together, those 3 telescopes would reduce substantially the blind region that we now have from Earth observatories. And as a further enhancement, we duplicate all of that on Venus and Venus orbiters. So together, the Venus and Mercury orbiters will reduce the solar occlusion volume to a tiny shadow of its former self and vastly improve our capabilities to detect these troublesome objects. Now, all of this will require some artificial intelligence. And if we can operate cars through artificial intelligence, I claim we should certainly be able to operate a series of space observatories in the same fashion. We're fighting with time for the electronic signals to go over and back. I even advocate for another set of comet threats, having a similar type of operation in the vicinity of Jupiter. And for a Jupiter telescope, it would take a minimum of an hour just over and back to get your electronic messages. So we have to delegate some decision making to these space stations themselves, and artificial intelligence would be the medium for doing that. So I had a longer talk, but I have a paper that is accompanying this talk. And the paper is the one that we're presenting right now. And I'll be happy to send this paper to anybody who's interested. Just send me an email to this address. My name is Lapin, and the email address is Lapin, L-A-P-I-N, initial L, that's my first name, lapinl@aol.com. And then I will send you a PDF file of this complete talk, which is much more detailed than I can give you now. So with that, I'll conclude my talk because we've run out of time. But if you have any questions, I'll try to answer them, and we'll do it through the electronic means with the chat room and so forth. And I'll do it in writing. Thank you very much.
Well, thank you. That was an unexpected extra dimension on other uses for astronomy and in keeping us all safe and maximizing our future prospects. And that paper sounds very interesting, and look forward to seeing it.
Great.
And I see the Kelsey, you said that there are questions on the queue there under Q&A. Most of them looks like they're for Dr. Burns, but I think if there are no other questions, I think we'll conclude our session on astronomy from the moon, if that's protocol.
Yeah, we're just about at time. Steve, I'm not sure if you were able to see the questions for you a while ago in the chat box. It was like a few minutes after your talk ended.
I did see
Okay.
one. I didn't, and I tried to answer it briefly on meteorite impact.
All right, great.
On lunar observatories, but thank you very much. Appreciate your help and that of Dan as well, and very much appreciate Dr. Chen, Linji, Jack Burns for his great and exciting presentation, and the extra dimension presentation from Larry Lappin. And thanks so much for AAS to give us this opportunity. And Kelsey, thanks for your staying with us, seeing we go through correctly all the way beginning to end. Thanks so much.
And Steve, thanks for organizing the session.
Oh, my pleasure. Thank you, Jack, for helping making it so productive. And we'll be following on, I'm sure. So if that's it, are there any protocols for concluding the session, Kelsey, or should I just say aloha? And thank you all very much.
I'm actually not sure, Dan, what is the protocol for concluding a session?
I think aloha is perfectly appropriate.
Okay.
Okay, thank you all. Have a good day and good productive week, and good conference AAS 236. Thank you.